Welcome to this lecture of partial derivatives. In this lecture, we will study about the higher order partial derivatives and take the Clairaut theorem. Now, before starting the higher order partial derivatives, we shall recall what we mean by a partial derivative of a function. So here we have a definition. Given a function f of x, y, a function of two variables, we can then define two partial derivatives of f with respect to x and with respect to y. So these two first order partial derivatives are fx, which is defined as a limit when h goes to 0, f of x plus h, y minus f of x y divided by h. So in the partial derivative of f with respect to x, we take a change in x, and similarly a partial derivative of f with respect to y, we take a change in y, which is so defined as limit k tends to 0, f of x y plus k minus f of x y divided by k. Now obviously the higher order partial derivatives will be defined by taking the derivatives of these derivatives. Now when we take a derivative of f with respect to x, we will get a function of x and y, and we can take the partial derivative of this function with respect to x as well as with respect to y. And similarly, when we calculate fy, which will again be a function of x and y, then we can again take a partial derivative of f with respect to x as well as with respect to y. So in this way, we will obtain four partial derivatives of f with respect to x and y. Now they will be called as the second order partial derivatives, and we will define them in this way. So we have here second order partial derivatives. Now first of all, we take a second order partial derivative of f with respect to x, which can be defined as del f by del x of fx. So therefore, this can be taken as in the form of a notation like fx, which can be defined as limit h tends to 0, fx at x plus h comma y minus f of x y whole divided by h. Now similarly, we can take a partial derivative of fx with respect to y, which we can denote by del y of fx, which we can also take as fxy. So therefore, this is defined as the limit like k tends to 0, fx of x comma y plus k minus fx of xy whole divided by k. Now next we can also take a partial derivative of fy with respect to x, which we can denote by del f by del x of fy, which we can denote by del yx, which is equal to limit x tends to 0, fy of x plus h comma y minus fy of xy whole divided by h. And similarly, finally, we can define del y of fy, which we can denote by fyy, and can be defined as limit k tends to 0, fy of x comma y plus k minus fy of xy whole divided by k. So these are the four second order partial derivatives of f with respect to x and y. Now here we can denote this first, which is fxx. This can also be denoted by del square f by del x square. Now this one can be denoted by del square f by del y del x, which is fxy, and this one can be denoted by del square f by del x del y, and this one can be denoted by del square f by del y square. So these are the second order partial derivatives of f with respect to x and y. Now let's take one example. Find this fx, fy, fxy, fyx for the function f of xy is equal to xy plus x cos y. So in the solution, we have first of all fx, which is equal to del by del x of fxy. So therefore, this is equal to del by del x of xy plus x cos y. Now when we are taking the partial derivative of a function with respect to x, we will treat all the other variables as constants. So why will we treat as a constant in this definition? So derivative of this function with respect to x is y plus cos y. because derivative of x will be equal to 1 with respect to x. And similarly, we can define del fy, which is equal to del by del y of f of x y, which is now del by del y of xy plus x cos y. Now with respect to y, we will treat x as constant, so the derivative will be equal to y plus, now x here, derivative of cos is equal to minus sine, so this becomes minus x sine y, because x is treated as constant. Now therefore we can take fxy, which we can take as del by del y of fx. So therefore this is equal to del by del y of, now fx, as we have already defined it as y plus cos y. Now derivative of this function with respect to y is 1 minus sine y. And finally fyx, which we can define as del by del x of fy. So this is equal to del by del x of, and fy is equal to y minus x sine y. Now derivative with respect to x will be, the derivative of the first term is 0. So we made a little mistake here. So instead of y here, when we are taking the derivative with respect to y, we will treat x as constant. So therefore it's x minus x sine y. And here we will get 1 minus sine y. So in this way we have evaluated all the second order partial derivatives as I asked. And similarly we can obviously evaluate fxx and fyy. Let's calculate them in addition to what was asked in the question. Now fxx is equal to del x, del by del x of fx, which is equal to del by del x of y plus cos y. So this will be equal to 0. And similarly fyy, this will be equal to del by del y of fy, which is equal to del by del y of x minus x sine y. Now treating x as constant, we get the derivative as 1, sorry, this is 0 minus cos y. So these are the four second order partial derivatives of f with respect to x and y. Now here we can actually notice one thing, that fxy is equal to fyx. So the partial derivative of f with respect to x and then with respect to y is 1 minus sine y. And partial derivative of f first with respect to y and then with respect to x is again equal to 1 minus sine y. So here we make one notice. We have this fxy is equal to fyx in this case, and this is equal to 1 minus sine y. But the question is here, is this always true? So we will ask a question here, is fxy equal to fyx always true? So this is our question, but the answer to this question is no. This is not always true. Then the next question is, what are the conditions under which these are true? So they are the conditions which are given by the Clairaut's theorem, but before that we will take up an example where we will see that fxy may not be equal to fyx. So let's take up this example. So consider a function f of xy, which is defined in this way: xy and x square minus y square whole divided by x square plus y square, when this xy is not equal to 0, and second, this is defined to be 0 when xy is equal to 0. Now our question is, evaluate fxy at 0, 0 and evaluate fyx at 0, 0. So let's come to the solution. First of all, we evaluate the first order partial derivatives, and then we can evaluate the second order partial derivatives. We have by definition, suppose this fx, this is defined as limit h tends to 0 f of x plus h comma y minus f of xy whole divided by h. And similarly, we can take the definition of fy. Now let's evaluate the first part, that is fxy. Now fx at suppose 0 comma y, this is equal to limit h tends to 0. Now substituting this in this function, So we will get f of h comma y minus f of 0 comma y, because x is taken to be equal to 0, whole divided by h. Now substituting the value of the function, so this gives limit h tends to 0. Now f of hy, that will be equal to hy into h square minus y square whole divided by h square plus y square minus. Now in the given function, when we evaluate f of 0, 1, that will be equal to 0, and we have whole divided by h. Now let's simplify this. This is equal to limit h tends to 0. So now this h and this h gets cancelled. So we are left with y into h square minus y square divided by h square plus y square. Now in this function, when we let h be equal to 0, we get minus y cube divided by y square, which is equal to minus y. Therefore, the partial derivative of f with respect to x at a point 0, y is equal to minus y. Hence, partial derivative of f with respect to x at a point 0, 0. So therefore, this is equal to 0. It can be obtained by just putting this minus y equal to 0. Now on similar lines, similarly, when we evaluate fy at x, 0, so this will be equal to limit t tends to 0 f of x, k minus f of x, 0 whole divided by k. Now using the values of the function f of x, y, we get this limit k tends to 0. Now f of xk, that will be equal to xk into x square minus k square whole divided by x square plus k square minus 0, because f of x 0 will be equal to 0, whole divided by k. Now simplifying this again, so this becomes limit k tends to 0. Now this k will be cancelled with this k, so we are left with x into x square minus k square whole divided by x square plus k square. When we let k tend to 0, we get x cube divided by x square, which is equal to x. So fy at x 0 is equal to x. Hence we can easily evaluate fy at 0, 0. So therefore this is equal to 0. So here we can see that the first order partial derivatives of f with respect to x and y are both equal to 0 at 0, 0. Now let's evaluate the second order partial derivatives. So now partial derivative of fy with respect to x at 0, 0 is. So this is with respect to x, so we can denote it by del x of fy, which we can actually write as fy x at 0, 0, which is defined as limit. Now since this is partial derivative with respect to x, and then we write the limit h tends to 0. Now it is the partial derivative of fy, so it is fy of 0 plus h, 0 minus f of 0, 0 whole divided by h. So we can write this is equal to limit h tends to 0 f y of h, 0 minus fy of 0, 0 whole divided by h. So this is equal to limit h tends to 0. Now we have already evaluated what is fy at x0. Fy at x0 is equal to x. So fy and fy at 0, 0 is equal to 0. So this means fy at h0 will be equal to h minus fy at 0, 0 is 0 whole divided by h. So we get this is equal to 1. Similarly, like this fxy at 0, 0, which we can also write as del by del y of fx, which we can define as a limit k tends to 0 fx of 0, 0 plus k minus f of 0, 0 whole divided by k. So this is equal to limit k tends to 0 fx of 0k minus fx of 0, 0 whole divided by k. So this is equal to Now fx at 0 y, that was already calculated to be equal to minus y, so this becomes limit k tends to 0. So this fx of 0 k is minus k minus fx of 0 0 is 0 divided k, so this is equal to minus 1. This fx of 0 k, so this was actually fx at 0 y, that was equal to minus 1, so fx at 0 k is equal to minus k. So here we can therefore see that fyx is plus 1 and fxy is minus 1. So therefore, thus fxy at 0 0, this is equal to minus 1, and fyx at 0 0, this is equal to plus 1. Hence we can see that fxy is not equal to fyx. Therefore, fxy at 0 0, this is not equal to fyx at 0 0. Therefore, we have a case when these partial derivatives are not equal. Now we take a theorem that we call the Clairaut theorem, which teaches us under what conditions we have fxy is equal to fyx at a point. So we have the Clairaut theorem here. The theorem states that if a function f of xy and its partial derivatives, which are fx, fy, fxy, and fyx, if these partial derivatives are defined at ab, at a point ab, and are continuous at this point a comma b, then the mixed partial is del square f by del x del y at this point a comma b. This is equal to del square f by del y del x at the same point a comma b. So therefore, the condition for which under which the mixed partials are equal, the conditions are that the function itself should be defined and continuous at the point ab, and it is partial derivatives which are fx, fy, and fxy, and fyx. They should all be continuous at the point ab. Then the second order mixed partial derivatives will be equal. Now let's take the proof of this theorem. For sufficiently small h positive and k positive, so we have chosen the real numbers h and k as infinitesimals. We define a quantity which is denoted by del at k, which is defined in terms of the function f, and defined in this way: f of a plus h, b plus k, minus f of a plus hb, minus f of a, b plus k, minus f of ep. So this is just a notation, and we call this expression on the right hand side as simply del hk. So this is sometimes also known as the auxiliary expression or auxiliary equation. Now define a function g of y. G of y is a function defined in this way. This is f of a plus h, comma y, minus f of ey. But then we can clearly see that this function on the right hand side is a function of y, and we denote this function of y by g of y. Then we can see that this g of b plus k minus g of b, then this is equal to, now first of all, g of b plus k. We have to replace this y by b plus k everywhere. So we get f of a plus h, now y will be replaced by b plus k, then minus f of a, again y will be replaced by b plus k, then minus. So this is the first expression, then minus g of b, and g of b will be equal to f of a plus h, comma y, but y is equal to b, so this is comma b minus f of a comma b. So therefore we have the function g of b plus k minus g of b, but we can see the right hand side expression is exactly delta of hk. So this is equal to delta of hk. That means for the function g of y, we have g of b plus k minus g of b. This is equal to delta of hk. Now since we are given that the partial derivatives of f with respect to x and y, they exist and are continuous, so we write like this: since fy exists, since fy exists. Thus, when we take a derivative of this g of y, it will be equal to fy at a plus hy minus f of ay. So when fy exists, therefore the derivative of this g exists. So this g dash of y exists. Hence by Lagrange's mean value theorem, there exists a point, and we shall call this point as b1, which belongs to the interval b comma b plus k, such that this g dash of b1, this is equal to g of b plus k minus g of b whole divided by b plus k minus b. And the expression on the right hand side can be clearly seen to be equal to g of b plus k minus g of b whole divided by k. So this gives us this g of b plus k minus g of b is equal to k times g dash of b1. This is equal to k times. Now what is g dash of b1? We have the function g of y is equal to f of a plus h comma y minus f of ay. Therefore we take a derivative of this g with respect to y on both the sides, and this can be written to be equal to del by del y of f at a point a plus h comma b1 minus del by del y of f at a point a comma b1. Let's call this equation as equation number 1. So now consider another function. Now consider a function which is defined as fx is equal to del by del y of f of x comma b1. So actually looking at these two expressions, we have del by del y f of a plus h comma b1 and del by del y f of a comma b1. So for these two expressions, we will define another function which is denoted by capital F of x equal to del by del y of f of x comma b1. And this function is defined on the interval a to a plus h. Now if we take the derivative of this f, it will be the second order derivative of this small f. So then since del f del square f by del x del y exists, since this exists, we have this f dash of x exists. Therefore, we can apply the Lagrange's mean value theorem to the function f of x. Thus, by Lagrange's mean value theorem, we have this f of a plus h minus f of a whole divided by a plus h minus a. This is equal to f dash of a1 for some a1 belonging to the interval a to a plus h. Now let's substitute the values of this f of x, since it is defined as the del f by del y of f of x b1. So therefore this f of a plus h, we can write this as del by del y of f at the point a plus h, which is like a plus h comma b1 minus, now f of a, this will be equal to del by del y of f at a comma b1, now whole divided by h. Now on the right hand side, we can write this as h times, now f dash, this will be equal to del square f by, or we can write it as del square by del x del y for the function f at the point a1 comma b. Now let's call this as equation number 2. Now if we look at equation number 2, so then substituting this left hand side for this expression equation number 2, then we get, now from equation 1, we obtain, we have, let's look what was our equation number 1. So it was g of b plus k minus g of b, which was equal to k times the expression on the right hand side is exactly the expression on the left hand side of equation number 2. So therefore we get this we get g of b plus k minus g of b is equal to k times this expression, which is h del square by del x del y of the function f at the point a1 comma b1. So that is this g of b plus k minus g of b is equal to hk times del square f by del x del y at the point a1 comma b1. But we know the expression on the left hand side, g of b plus k minus g of b, this is delta of hk. So that is this delta of hk is equal to hk times del square f divided by del x del y at the point a1 comma b. Let's call this equation as equation number 3rd. Now if we look back into our proof, we have obtained this equation number 3rd by defining a function g, which was defined as g of y is equal to a plus f of a plus h comma y minus f of a y. On similar lines, we define a function h of x, which is defined as f of x comma b plus k minus f of x comma b. Then again h of a plus h minus h of a. This will be equal to delta of h comma b. And the function, since the first order partial derivatives are continuous, therefore the function h will be differentiable. So we can apply the Lagrange mean value theorem on the function h, and then we will obtain the expression which was obtained here, the expression like this equation number 1. Then again applying the Lagrange theorem on the right hand side of the equation for the function del by del y f of this function and del by del y f of a comma b1, we will obtain the equation number 2. So exactly using the similar procedure that we have obtained, that we have applied on the function g of y, we will obtain this expression. So then the function h of x gives this delta of hk is equal to hk times del square f by del y del x at some point a2 comma b2, where this point a2 belongs to the interval a to a plus h, and point b2, this belongs to the interval b to b plus k. So we have now two equations. One is equation number 3 and another is equation number 4. But for these two equations, equation 3 and equation 4, we have the same left hand side, which is delta hk. So we can compare the equations 3 and 4. So comparing equations 3 and 4, we obtain this hk times del square f by del x del y at some point a1 comma b1. This is equal to hk times del square f by del y del x at a point a2 comma b2. But we need the second order mixed partial derivatives to be equal at the point a comma b. Now we have these a1 comma a2. They belong to the interval a comma a plus h, and the pointers b1 comma b2. They were chosen from the intervals b to b plus k. Therefore, as h comma k tends to 0 comma 0, we have these two points. a1 tends to a, a2 also approaches a, and similarly b1 approaches b, and also b2 approaches b. Therefore, if we look at this expression, which we shall call as equation number 5, then the point a1 will approach a when h tends to 0, and b1 approaches b when h tends to k tends to 0, and so on. Therefore, we take the limiters. So hence limit hk then approaches 0 comma 0, we get this del square f by del x del y at the point a1 comma b1. This becomes equal to limit hk tends to 0 0 for the function del square f by del y del x at the point a2 comma b2. Now, as the second order partial derivatives are also continuous and they exist, so therefore these expressions on the left hand side as well as on the right hand side exist. And as hk tends to 0, a1 b1 approach a comma b and a2 b2 also approach a comma b. So thus we obtain, so noting that fxy and f by x are continuous at the point a comma b, therefore we can say limit h tends to 0 0 del square f divided by del x del y at a1 comma b1 is simply equal to del square f by del x del y at a comma b. So we have to use two things here. One, that when hk approaches 0 0, this a1 b1 will approach a comma b, and since function fxy is continuous, therefore del square f by del x del y approaches simply del square f by del x del y at the point a. So therefore we have del square f by del x del y at AB is equal to del square f by del y del x at the point AB. So this completes the proof of Clairaut's theorem.